These are all perfect squares. On the left-hand side, they're multiplied out, and on the right-hand side, they're in factored form. What are some of the patterns that we see in these perfect squares? Well, some of the things that I see are the following. First of all, I noticed that in each one of them, the first term is a perfect square. I can tell that because even when I read them, I have to use the word square. X squared, y squared, w squared, and a squared. Those are all perfect squares. Similarly, the constant on the end, the last term, is a perfect square. 1 is a perfect square. It's the square of 1. 4 is a perfect square. It's the square of 2. 9 is a perfect square. It's the square of 3. And 16 is a perfect square. It's the square of 4. But that's not enough to have a perfect square. You have to look at the middle term as well. The middle term has to be equal to double the product of the square roots of the first and last terms. That's a lot of words, but all it means is once you've established that the first term is a square, and here we see it is, it's the square of x. We write down x. The last term is a square. It's the square of 1. We write down 1. Then we look at the two things we wrote down, x and 1. We, in our mind, multiply those together. That gives us x. And then we double. That gives us 2x. If that's the same as this middle term, then what we have is a perfect square, and that's how you factor it. That's why I think it's a good idea to write down those two square roots, because if it's factorable as a perfect square, you're writing down part of the answer. Let's check for this second one. The first term is the square of x. The last term, the number, is the square of 1. So now let's take that x and that 1 and multiply them together. We get x. And now notice that I put a minus sign there because there's a minus right here. Okay? So when I multiply x and minus 1, I get negative 1, and I double that, and I get negative 2. That's why I have to put a minus sign right here, because there's a minus sign over here. At any rate, you see that the middle term is, once again, double the product of the x and the minus 1. And now we have the factored form. Let's look at the third one. Y squared is the square of y. 4 is the square of 2. There's a plus right here, so I put a plus right here. Now in my mind, I multiply y times 2, that gives me 2y, and now I double it, that gives me 4y. I guess I wrote the problem down wrong. I think I really wanted to write a y right here, so let's just change it. Okay, now it matches 4y. And so once again, got a perfect square. Continue. W squared is the square of w. 9 is the square of 3. That is a plus, so that is a plus. W times 3 is 3w. 3w doubled is 6w. That's the middle term. Therefore, this is the correct perfect square. Now let's look at the last one. A squared is the square of a. 16 is the square of 4. This is a plus sign, so I put a plus sign here. In my mind, I multiply a times 4. I get 4a. Now I double that, gives me 8a. That is the middle term. Therefore, this is a perfect square, and that's the factored form for the perfect square trinomial. Now that you know how to identify a perfect square, let's see if you can complete a square. Let's suppose that we have the first two terms of our polynomial, and they are x squared plus 12x. What do we need to add to this so that what we have is a perfect square? Well, remember, if it is a perfect square, it's going to have a factorization that looks like this, because that's what a perfect square is. Since this is x squared, the only choice we have for here is x. Since this is a plus sign, we have to put a plus sign here. Now we have to figure out what number goes here, so that if we take that number times x and then double, we get 12x. So what do you think that number has to be? So that when you take that number times x and then double, you get 12. I think it's pretty easy to see that number has to be 6. If that number is 6, then what number goes here? Well, the number that goes there is the square of 6, and that's 36. That means we have completed the square for the polynomial, and the factorization is x plus 6 squared. Now this is useful when you're working with equations of circles when the formulas are not given in the standard form. So let's see how we can use completing the square to show that we have the equation of a circle. What if we have the equation x squared minus 2x plus y squared plus 8y plus 1 equals 0. That's an equation. It has two variables, and it's not apparent right away that this is the equation for a circle. And that's because the perfect squares have been multiplied out and terms have been collected, and so everything has been all mixed up. And what we need to do is unmix it up, but we can't change the balance of this equation. So if we add any numbers on one side, we have to add the same numbers on the other side, because what we have here is an equation. Let's begin with the polynomial in x. That's x squared minus 2x. Those are the x terms. So x squared minus 2x. We have to think about what we have to add to this so that what we end up with is a perfect square. We also have to keep in mind that whatever we add here on the left-hand side, we're also going to have to add over here on the right-hand side, which right now only contains 0. Okay, whatever we put here, remember, our factorization is going to look like this. X, because this is x squared, minus, because that's a minus, and then some number, and whatever number we put here, remember when we multiply this number times x and then double it, we should get negative 2x. Well, that means this number must be 1, because if we multiply negative 1 times x, we get negative x, and we double that, we get negative 2x. So we got the right number. What number do we put here? Here we put the square of the number we wrote here. We wrote a minus 1, so when you square that, you get a plus 1. Now we just added 1 to the left-hand side of this equation. But since this is an equation and we want to stay balanced, we now have to also add 1 to the right-hand side. Do the same thing to both sides. We've now completed the square on the x part of our equation. The next step is to complete the square on the y part. So we have y squared plus 8y. And we also have this plus 1 that I want to write down because I don't want to forget about it. That plus 1 was part of the original equation. It has nothing to do with the completing the square part. That was this one right here. It's on the original equation, and I have to keep track of it. But here is where I'm going to add the number that's going to complete the square on y. So let's think about what that means. That means that we have to have y here because we got y squared. We have a plus here because that's a plus. And remember, the factorization is going to look like this, and we need a number here such that when we multiply that number times y and then double, we get 8y. Well, I think you pretty much can figure out that number has to be 4. If that number is 4, the number we put in the blank here is the square of 4. Remember, we're doing a perfect square, so the square of 4, 16. But we just added 16 to the left-hand side. We've got to balance our equation and add 16 to the right-hand side. Okay? So now we have, for our equal sign, on the other side, we have 0 plus 1 plus 16, which is 17. And look, we now have our equation in the standard form for a circle. We know the center is h, which is 1, k, which is -4. And remember, this is r squared, and so therefore r is the square root of 17. Now I hope this helps you with the rest of handout for section 1.2. Look for something soon for handout on 1.3.